In this video, we're going to be looking at metamorphic rocks and how to classify them. So a good question to ask yourself here is, why does metamorphism occur in the first place? So we asked this exact same question when we talked about weathering of rocks, and the answer is exactly the same. These rocks undergo metamorphosis here because they're undergoing some sort of change in environment. They're going from a place where they're stable to becoming unstable under new conditions. And so under those unstable new conditions, they start to change again to become more stable. This really is the other side of weathering. Here's a beautiful example of some metamorphic rocks for you. At the bottom of the Grand Canyon, down in the inner gorge, you find the Vishnu Schist. That's the dark rock you see beneath the layers. There's little pink swirls in there. That's actually the Zoroaster granite. Those are little dikes that are swimming through there. But the Vishnu Schist is one of the oldest rocks in Arizona. So a parent rock, or a protolith, is the pre-existing rock that undergoes a solid state change in response to the modification of its environment. Protolith comes from a proto, as in prototype, means before, and lith means rock. So it's the rock it was before. So to make a metamorphic rock, you have to change some other rock. So that parent rock is that original rock we're changing. And these often look like they're parent rocks. For instance, on the left, you have a granite, which is an igneous rock, and on the right, you have a gneiss, which is a metamorphic rock. And in both of those, we can recognize similar minerals like biotite, like potassium feldspar, and like quartz. But you can see there's a definite difference between the two. So what do you see that's really different between these that might tell you one is metamorphic? Hopefully you notice that this sort of has layers, right? So what can you do to a granite to give it layers like that? Well, you can squeeze it. And that's exactly what happens there. So that's a beautiful gneiss. It's a German word, so I would say it's a nice as in G, that's a nice rock. Now the things that are changing in the environment that make rocks need to metamorphose. We call these the agents of metamorphism, although I often think this would make a nice title for a superhero comic book series, right? Alright, so the first one is heat. So how are rocks heated? Well, it comes from two main places. One is the fact that the earth is just hot. It gets hotter as you go down deeper into the earth. So one of it is the geothermal gradient. This is the rate of change in temperature at depth in the earth. Or it can also happen due to igneous activity in the form of plutons, like you see these blobs of magma underground, or volcanism. It's happening at the surface. So those are the two main ways that you get heat. Pressure is the second agent of metamorphism. So what squeezes rocks? What puts pressure on them? Well, there's two main places this comes from. You can have pressure, this is confining pressure, also known as lithostatic pressure. Litho means rock. So this is just the weight of the overlying rocks and all the rocks around it. We call this a confining pressure because it's the same in all directions. It's being squeezed sort of equally from everywhere. On the other hand, we have differential stress. And in differential stress, there's higher pressure from one direction than others. So the force isn't equal all the way around. So in this case, this is compressional because it's being squeezed. You can also have shear differential stress, which kind of smears things. I'll show you examples of those as we go. And last but not least, we have chemically active or hydrothermal fluids. So where do we get hydrothermal fluids? Hydro means water. Thermal means hot. So basically it's a lot of hot water. You also get quite a bit of carbon dioxide too. So where do these come from? Almost all of these are actually coming from, being released from igneous intrusions. And here's an example when we talked about igneous rocks, we looked at how much volatiles that's actually dissolved in magma. And remember, that was the gas component. But that gas component doesn't go into chemical structure. So as your magma cools and forms igneous rocks, the leftover magma becomes more and more enriched in these volatiles. And eventually, they end up getting squeezed out and they'll follow along faults or veins. And what we're going to see is this is actually pretty important for Arizona right here. All right, so those are your three agents of metamorphism. Now, you don't always have a lot of each of these, right? So the metamorphic grade is a way to identify the intensity of metamorphism. The higher the heat and the pressure, the higher the metamorphic grade. So more heat, more pressure is applied to it, the higher the grade is. In general, this equates to larger mineral crystals within the rocks. So some of the things you can do to identify your metamorphic grade is to find specific minerals, and that's what this chart here is showing. So at the top, we start with just plain old sedimentary rocks. All right, so this has clay minerals. If you remember, clay minerals were a result of hydrolysis. So under low pressure, low temperatures, those clay minerals can metamorphose into chlorite, which is a green mineral, or even white mica or muscovite. All right, so that's usually, that chlorite's usually a very good indication that you got fairly low grade metamorphism. If you squeeze it a little bit more, you're going to get bigger and bigger muscovites. You squeeze it even more, you're going to start to get biotite and starlite. You squeeze it even more, you get garnets. And then finally, you can get sillimanite and potassium feldspar. Remember, potassium feldspar actually weathers to make clay minerals. So it's kind of, like I said, two sides of the same coin. And so the types of minerals, you can always also look at a facies. And if you remember, we had sedimentary facies. Those are rock types that all form in the same conditions. We also have metamorphic facies. And so this is looking at the type of rock that's formed under certain conditions. If you look, temperature is increasing to the right, pressure is increasing down, which makes sense because pressure increases as you go down in here. At these kind of low pressures and temperatures, there's no metamorphism. It's not high enough of either one of those. If you get a little bit higher, if it stays fairly low pressure but it gets hotter and hotter and hotter, this is called contact metamorphism. If you're increasing both pretty easily, that's mountain belt or regional metamorphism. And then if you're increasing pressure but not temperature, this is subduction metamorphism. This is where we form blue schist, and we're going to look at that here in just a little bit. Now, of course, if the temperature gets a little too high in this high grade, things start to melt. And at that point, it's no longer metamorphic anymore, but now the rocks are igneous. We can also see this reflected in geology too, if we look at a large area. So this is the east coast of the United States. This is metamorphic rocks that were formed when Pangea all came together and smushed everything there. So in that continental collision, we actually had a rather large belt of metamorphism. So if you look down the middle of the belt, you get cordierite and sillimanite, or orthoclase, that is potassium feldspar. So your highest one is in the center here. Then sillimanite and muscovite's a little bit lower grade. Then kyanite is a little bit lower grade. Then andalusite, a little bit lower grade. Then garnet. Then biotite chlorite here on the edge. And then finally, no metamorphism at all. So you can see that increasing pressure as you go to the interior of that particular set of mountains. So that's reflected here as well. So your highest temps to higher pressure, which means your highest grade metamorphism, is going to occur in the very middle of this continental collision. In that case, you're going to have the very highest grade metamorphic rocks. So we're going to come back and look at these separately, but that's where you get a gneiss. Over here on the edge, where you have very low temperatures, very low pressure, this is where we find the low grade metamorphic rock slate. And of course, it's transitions in between the other ones in the middle there. We have to talk about metamorphic textures. So if you remember, the texture of a rock is the size, shape, and orientation of minerals. In igneous rocks, we looked a lot at the size of the minerals because the slower it cooled, the bigger they were able to grow. In this case, we're going to look at the size. We're also going to look at the orientation. So I want you to imagine this is a granite. And I sort of blurred out everything but just the biotites. And I'm going to squeeze those biotites. Watch it squeeze. So notice what's happened here. All of those biotites have turned and lined up with each other. This means they have a preferred orientation. This alignment of minerals is known as foliation. This comes from the same word as foliage, which comes from the root word for leaf, because it all flattens out and lays flat on top of each other. You can also recognize foliation as parallel surfaces or layers in metamorphic rocks. So foliation is a result of both pressure, as you just saw, and composition. So minerals that are going to often foliate are ones that have preferred orientations, like biotite and muscovite, or even amphibole. But because of their shapes, minerals like quartz, which forms blobs, or minerals like calcite, which forms rhombohedrons, don't have a preferred orientation and therefore don't foliate very well. So foliated metamorphic rocks are going to be classified based on the size of the minerals. We're going to work our way up from the smallest crystal size to the very largest. This also works our way up in metamorphic grade, because the lowest metamorphic grade here is slate, and it has very small crystals. The higher the metamorphic grade, in this case, the larger the minerals get. All right, so slate. Slate is our finest grained metamorphic rock. It's a very fine grained rock. You're not going to be able to see any of those minerals in there. That being said, the rock tends to look kind of dull. It doesn't reflect light very well. But you've probably heard of slate before in terms of maybe slate tiles for roofing or for flooring, or even a slate chalkboard. You may, if you have a really nice pool table, the pool table surface might be made of slate that's covered in felt. So when slate breaks, it breaks along really flat layers. That's why it makes these tiles on the roof so well. It's because it's very, very flat. Now, since it's fine grain and metamorphism tends to make minerals larger, you need a really, really fine grained rock as a parent rock. So common parent rocks for slate include mudstone or volcanic ash. And oftentimes, slate and mudstone look a whole lot alike. It really is just how flat the layers are that makes slate recognizable. And in the image on the left here, you can see that these are from a slate quarry. And those blocks look just bizarrely flat, like somebody might have cut them that way or poured concrete that way. But this is actually how the slate breaks. A phyllite or a phyllite, either pronunciation I will buy. This is fine-grained as well, but it's not quite as fine-grained as the slate. So the crystals aren't big enough to see, but they are big enough to start reflecting the light just barely. We say it has a glossy sheen to it. I've often heard it described as being sort of like the glaze on a donut. It's not shiny, but the light just barely catches it. If you're into painting, a slate would have like a flat finish, whereas a phyllite has like a satin finish for paint. Just barely picks up the light. Instead of making the really flat layers like we saw in slate, phyllite breaks off into wavy layers. Just a little bit of waves to it makes it easy to recognize. Now, the most common parent rock for phyllite is a slate. Now you're like, that's already metamorphic, but exactly. So what we're going to do is we're just going to take that same mudstone, add a little bit of pressure to it, you get slate, add a little bit more pressure to it, and you get a phyllite. Now one of my very favorites is a schist. It also makes for great geology puns. So schist is coarse grained. The crystals are really big, you're going to be able to see them. And a lot of times you're going to see a lot of biotite, lots of muscovite. Every once in a while a whole bunch of amphibole. Those are big minerals to recognize in these. So in this case the crystal size is coarse grained. And all of those mica minerals, like muscovite and biotite, they tend to align and lay down flat on top of one another. And so it often makes me think of fish scales. So what kind of rock can we get these big, beautiful crystals out of? How about a phyllite? Of course, the parent rock of a phyllite is a slate, and the parent rock of a slate is a mudstone. So you can start off with a lowly little mudstone and get this awesome schist out of it. Now, one of the easiest ones to recognize is our highest grade of foliated metamorphic rock. This is a gneiss. And again, this is a German word, as in G, that's a gneiss rock. These are coarse grained. They have large crystals. And you can recognize that because you can actually see two different colors of minerals, just like when we talked about igneous rocks. The key to this, though, is things have been so squeezed that those minerals are starting to segregate out. And so you get stripes of color in a gneiss. You've got stripes of a dark mineral that's probably amphibole or pyroxenes. You've got stripes of white that's likely plagioclase feldspar. So what's the parent rock of a gneiss? Well, it could be a schist. So we add just a lot of more pressure and heat to a schist and go straight up the rest of those. Or oftentimes your parent rock is either diorite or granite. And in this case, this was probably a diorite, because if you look at the similarities between the metamorphic rock and this igneous rock over here, they do look a whole lot alike. All right, and so here's a little picture of how these things start to grow and start to make those bands. It's all about ions moving around. Now, the thing to keep in mind here, and I mentioned this at the very beginning, this is all solid state, which means you go from a mudstone to this big, beautiful schist, nothing melts, nothing dissolves. It's a solid rock the whole time those crystals are growing, which I think is pretty impressive. Now here's this picture again, but it puts it again into perspective for you. You've got this low-grade slate that you find on the edges of mountain belts. A little bit closer to the middle, you have phyllites. A little bit closer to the middle, you have the schist. And then finally, in the very center of these mountain belts, you form gneiss. Of course, it goes mirrors on the other side going out. But you can always tell just where you are in the mountain belts by what type of minerals you have and what type of metamorphic rocks are there too. There's one last kind of cool rock that falls under the foliated category, but it's not exactly a metamorphic rock, but it's also not exactly an igneous rock, and a migmatite. These are going to form under very high temperatures in which gneiss begins to melt. So we're actually melting rocks, you can see in the picture, that started to melt and start to swirl. Now, out of these minerals that you see here, which minerals are actually going to start melting first? It's the light colored stuff, because that's the stuff on the bottom of Bowen's reaction series. So those start melting out and they leave behind the dark stuff, but it kind of all warps along with it. So again, this isn't officially one of the foliated rocks, but it falls under there the most nicely. And of course, there's your Bowen's reaction series to show you the order in which these happen. One other kind of cool foliated texture is called porphyroblastic. Remember, we had igneous porphyries, and those were igneous rocks with two different grain size. And in this case, you have the same thing, and it's under the right temperature and pressure conditions for large crystals of certain minerals to grow. In this case, this is a schist with these big, dark, kind of red-brown crystals. Those are garnets. So garnets are a metamorphic mineral. They can form sometimes under other conditions, but really, if you see garnets, you know it's a metamorphic rock, and these are one of the higher temperature, higher pressure minerals too. Here's an example of a porphyroblastic rock with the recently deceased Lee Allison. He's the former head of the Arizona Geological Survey. Great leader of that organization. It's a huge loss for Arizona and for the survey to lose Lee. But here he is in front of a beautiful porphyroblastic schist And those are actually big garnet crystals. Those are like grapefruit-sized garnets, which are lovely. This was on display during the Tucson Gem and Mineral Show a few years ago, although the seller still has quite a few of these laying around if you ever visit. So those are your foliated rocks. Let's look really quick at a couple examples of non-foliated ones. Now there's a lot of non-foliated rocks, but really you're going to see mainly two. Alright, so non-foliated rocks are classified based on their composition, what they're made of. Our first one is called quartzite. What do you think this is made of? It's made of quartz. Yeah, so this is mainly quartz, which begs the question, what rock have we talked about already that's made of mostly quartz that could be a parent rock? What about a sandstone? Remember, a quartz aeronite's made of over 90% quartz. So you take that lovely sandstone, some beaches, a lot of sand dune deposits. You squeeze them, squeeze them, squeeze them, and you make a quartzite. Now here's kind of an interesting question. Have you ever thought about how heavy the space shuttle is? Probably not. Well, out here in space, it doesn't feel that heavy since it's falling and you get that sensation of being weightless. But as it's taking off, you have the space shuttle. You have its large tank full of fuel. You also have the solid rocket boosters on the side full of fuel. That's a heavy thing. And how did they get this to the launch pad? Well, they use a thing called a crawler. There's a picture of it on the crawler. Here's a close-up of the crawler by itself, so you can see just how massive these are. Fully fueled, the shuttle itself weighs 4.4 million pounds. It can hold a 65,000 pound payload, and the crawler is almost 6 million pounds. So you add all those up, and that's like almost 12 million pounds all put together of stuff. And this drives from their main building out to the launch pad. Now, if you're rolling with 10 to 12 million pounds worth of stuff, are you going to be able just to trundle on down the nearest freeway? Absolutely not. So notice in this picture on the left, the crawler is actually moving on loose rock. This is kind of interesting. So this is made up of a river gravel from Tennessee and Alabama, mainly because those are pretty close to Florida where the launch pads are. But this is all crushed quartzite because it's got an amazingly high crush strength. It could carry all that rocket on it and only kind of break down slowly over time. You can see this is actually used from the crawler way, which is what they call the little roads going out to the launch pad. You see some of them are broken, go mechanical weathering. But it's able to support the weight of the rocks of that rocket, which is pretty awesome. Now, if you want to find some quartzite here in Arizona, there's an easy place to go. You can just go visit 4 peaks. In between the 2 peaks, there's actually a mine. So this is the Mazatzal quartzite. The top's 4 peaks. That's why there's actually 4 little humps there, is because those are all nice, hard, resistant quartzite. And this particular quartzite actually looks a whole lot like, whoop, there we go, this one. Notice it's a lovely kind of maroon purple color. Now, so if it's made mostly of quartz, what's a quartz that comes in purple? That is called amethyst. And there's actually an amethyst mine tucked in between a couple of the peaks. It's known as the 4 Peaks amethyst. They're actually highly sought after as a gemstone. The gemstones from here tend to be really red purple versus a more blue purple that you're used to seeing from the Afghanistan. There's a shot from inside of the mine. Now, it's privately owned. You can't get there, but there are places you can buy jewelry made of the Arizona 4 Peaks amethyst. All right, here's one other rock for you. Marble. You've heard of marble, right? One of the best things about it is it's soft, which is why you make carving out of it. So statues are carved out of marble. You don't get too many statues carved out of quartzite just because it's so hard to do. Now, marble, if I were to put a little bit of hydrochloric acid on this marble would start fizzing and bubbling like crazy because it's made of mostly calcite. So what's a rock we've already talked about that is made of lots of calcite that bubbles and fizzes under uh, in response to hydrochloric acid that could be a parent rock? Limestone. Here's a beautiful fossiliferous limestone. But we take a limestone and you squeeze it and you get marble. Now marble comes in lots of different colors. We're used to seeing white, but it can be gray, it can be green, it can be black, it can be pink. It all sort of depends on what else was in that limestone mixed up. So a little bit of mud tends to turn it different colors. But for the most part, don't worry about the color, just the reaction with acid. Alright, those are your metamorphic rocks. Those should be fairly easy to recognize.